subsurface is key to help the energy transition. Again, I remind you that pollution from fossil fuels has direct consequences on people's health. Tehran is one of the most polluted capital cities in the world with a population of 15 million. And the World Health Organization has said that several years ago that air pollution kills an estimated 7 million people worldwide every year. And as usual, low and middle income countries suffer the most. Probably that number is higher now. And the air pollution comes almost 95% from diesel fuel, gasoline, and burning of coal for power. This is an example of burning coal for power a decade ago in Romania. I mentioned Romania and Europe because Europe is working hard to try to reduce the amount of fossil fuels in their energy sources, and it's very difficult, but it probably has to be done. So how can we use the subsurface to help this? Well, we can use it for natural gas storage. That's widely used now for 60 years, since the first caverns were built in Saskatchewan, Canada, back in the 1950s. We can use it for carbon sequestration. We can use the subsurface for secure liquid and solid waste injection. We can use it for energy storage, pumped hydro, compressed air. We can store heat in the subsurface for use in the winter, and we can store cool energy, or we can store cold temperatures in the rock mass for use when it's warm. And of course, geothermal heat and power are possible sources of energy for the future. Natural gas, these are natural gas and shale oil wells in Texas. And natural gas, some people believe, can play an important role in the energy transition by replacing coal. And also natural gas as a fuel for vehicles is much less polluting than diesel fuel or gasoline. But we won't talk about natural gas in this presentation. It's fairly well known how to produce and store and distribute natural gas. But I will talk about subsurface biosolids injection as a means of safe treatment of biosolids and as a means of sequestering carbon. And if you can find the suitable reservoir with a cap rock and an ability to accumulate, then you can even recover the methane, which is part of the decomposition product. I'll talk about subsurface enhanced geothermal systems and sedimentary fluid heat systems. In sedimentary heat systems, we need fluids, large amounts of fluids. That means we're looking for porosity and permeability, and that's exclusively in sedimentary basins at depth. On the other hand, enhanced geothermal systems, we're trying to mine the heat in the rock itself, not the fluids. And we have to come up with better ways of drilling cheap wells rapidly and do multi-well stimulation to allow flow in the subsurface to mine the heat. Then I'll speak of subsurface energy storage methods, compressed air storage, pumped hydro, and very briefly, a mention of the possibility of heat storage and integrated geothermal systems. In carbon sequestration, everyone thinks of carbon dioxide sequestration, but it is feasible, it has been done, and it is far safer, if you can, to store carbon in the subsurface in solid form, because then it cannot escape. We can do that with biosolids injection. This is an image about 13 years ago of the world's first biosolids injection site in Los Angeles. I was involved in the engineering of this site, and this site has operated effectively for 13 years, injecting treated sludge deep into the subsurface. The sludge, human biosolids, are of course slurried with wastewater and injected at depths, in the case of Los Angeles, 1,300 meters deep, but any depth greater than 500 meters is probably acceptable. At those depths, there is natural bacteria present everywhere. And when you put in biosolids, it's food for them. So they start reproducing and eating the food. The process involves generation of some methane, some carbon dioxide, and water. The carbon dioxide is very soluble in water, so it tends to stay in the formation water. The elemental carbon, the residue, which contains 50% of the carbon that you put into the ground or more, it's permanently sequestered as a solid phase. It's coal. You're turning biosolids into a low-grade coal. The environmental risks are very low compared to other methods of carbon sequestration. And of course, if you can recover the methane that is produced, then no fossil fuel is involved. And if you do some calculations, you realize that for a city that is disposing its biosolids in this manner, you can dispose more than 400 kilograms per person per year of carbon dioxide equivalent. And this is done with subsurface oil field technology. On the left-hand side here, we see a wellbore that is vertical, simple, and we're monitoring the pressures and other things, and it can be used for injection of a slurry of biosolids into an appropriate formation. And on the right-hand side, I just show a typical geology above the injection site, which of course restricts vertical flow and allows the pressures to dissipate. A biosolids processing facility would look more or less like this. You've got trucks that are, or pipelines that are bringing the product to the injection site, where it is homogenized, brought to the right density, about 1.15 grams per cubic centimeter density, and then injected under hydraulic stimulation pressures deep into a site at depth. So this is the biosolids pod that is generated after some time. This is a geological trap for the methane so that we can recover the methane with that horizontal well that I've shown. And the project in Los Angeles was at a depth of 5,000 feet in a depleted oil reservoir. The project has gone very successfully. All dangerous agents in the biosolids, like heavy metals, chemicals, viruses, are permanently sequestered safely and treated at depth. The carbon sequestration is largely in solid form, so it's fully secure, and methane may be recovered. Of course, other waste materials can be added to this mix. This is an example of tank bottom sludge from the heavy oil industry in Alberta. And over the years, there have been many injection operations in Alberta to dispose of solids, such as these wastes, and the solids are disposed back into the reservoirs from which they came. Much of this solid material that you see here was actually produced along with the heavy oil. So in this case, we're returning it to where it came from. This is the site in Dury, which Dury used to be the largest heavy oil project in all of Asia, and huge amounts of wastes were created. So starting about 14 years ago, I was involved in this project as well. An injection facility was built. The wastes were trucked to the site, to that large black pit in the middle, from all around the oil field, slurried and injected at depths below the heavy oil deposit. This facility turned the dirty oil field from a dirty, contaminating operation to an operation that was almost zero liquids and solids waste emissions. Taiwan is a city of 5 million people. Taiwan has a biosolids disposal facility. Taiwan is growing, and the facility is under a bit of pressure. Can we use biosolids disposal in Taiwan? And I remind you that it's a slurry of wastewater and biosolids. So there's nothing going down but waste. And I remind you of the security involved in this process. As it turns out, Taiwan geology is excellent for the disposal of biosolids. If not directly in Taiwan, then close by. And by close by, I mean tens of kilometers. It turns out that in Shanxi, the geology is extremely well understood because of a rich coal mining history. And there are many sedimentary basins that have suitably permeable and suitably porous strata at appropriate depths to sequester all of the biosolids that you would put in. So instead of a facility that looks like this, you would have a facility 1/4 the size. And instead of putting all of that carbon dioxide into the atmosphere from these sludge treatment facilities, and then putting the sludge on farmland, it would go underground. To give you an idea of the cost of full biosolids treatment in North America, in Los Angeles, $125 per dry ton of biosolids is what it costs. So Taiwan, 5 million people, biosolids is certainly an option that should be looked at. And of course, as I mentioned, the geology of Shanxi is excellent, with a number of deep coal mines even that have been abandoned that could be also used for the placement of biosolid waste. Of course, this means engineering. This means that you have to manage the process properly. Managing the process properly means accepting that you're going to be injecting under hydraulic fracturing conditions, unless it's an old mine. If it's an old mine, then your injection pressures will be less. You have to find the appropriate site, and of course, they're very widespread in sedimentary basins, they're everywhere. You have to find the appropriate site where the pore pressures that you build up by injection dissipate rapidly to avoid regional pressurization. What is the limit for slurried solids injection into a single well? I can't give you an answer exactly, but in some injection operations that I've been involved with, we have in a single well put in 1 million cubic meters of materials. The amount depends upon your depth, your stress changes, your fracturing behavior, the containment, the geology of the system, and a number of other engineering factors. But of course, we monitor all the time to make sure that we are not impairing the infrastructure of injection. Geothermal energy has been talked about for many decades as being a potential great source of energy from the Earth's subsurface, but it's not that easy. In particular, a country like Canada is very cold. If you look at Canada, the only place where we can find steam in the subsurface, and it's not necessarily enough is in British Columbia, in the mountain ranges that are volcanic in origin. And we have never found a site that can be commercially developed yet. Exploration is still going on. So that means that Canada has very little potential for high-grade steam-type geothermal energy. And the same for all of Europe except maybe Italy and Greece, 95% of Africa, 95% of South America. There is no hot steam at shallow depths. And you can see here in this map of Canada that maps the heat energy at 6.5 kilometers deep, that most of Canada is very cold. But we see the Western Canada Sedimentary Basin, that gray, green, and orange streak. In that area, we have fluids that are warm enough and shallow enough that we can exploit them for geothermal energy. But if we want to do heat mining in the rest of Canada, we can't use sedimentary heat methods. We have to use methods of stimulating a very low permeability rock mass, a naturally fractured rock mass, so that we can circulate fluids and mine the heat. Just to remind you how cold Canada is, the capital city of Nunavut, one of our territories, is Iqaluit. And here are the mean temperatures for Iqaluit. You see that there's only 4 months that the mean temperatures are actually above 0 Celsius. In fact, in Iqaluit, heat is needed every day of the year in homes, but especially in the very cold periods of November to April. That's a key point. When most people think of geothermal energy, they think electrical power. But it's far, far more efficient if you can use the heat directly. So if you're using, if you want to generate electrical power, you might have to have fluids that are 100 degrees Celsius or 90 degrees Celsius. But if you're using the heat only, then if you had fluids of 40 degrees Celsius, you could certainly use them to heat homes quite effectively. But most people think of power. And the reason for that is that the geothermal projects that have been successful in the world, in Italy and Indonesia, Japan, the United States, have been in warmer climates where there is not as much of a need for heat as northern Canada, as Canada being a northern country. So typically in a said heat geothermal project, hot liquids are accessed by drilling wells. The hot liquids are pumped through a heat exchanger. And the reason for that is because the hot liquids are brines. They're sodium chloride and calcium chloride brines, and they have to be recirculated back, and you cannot put them through the equipment. So you have to have a heat exchanger. And then the power system, usually an organic Rankine cycle, has a turbine and a generator to create energy to put into the grid. However, the efficiency of these systems in terms of the thermal energy available in the fluid is on the range of about 15%, maybe a little bit more or a little bit less. If we use the heat directly to heat homes, the efficiency goes way up above 65, 75%, depending upon the design of the system. Here is the first said heat project for electrical power in perhaps, well, I don't want to say North America, but certainly Canada. It's called the DEEP project, DEEP. And you can go to their website and find very interesting information about the project. The boreholes are vertical boreholes turning to horizontal in the reservoir in order to generate enough flow capacity. More than 3 kilometers deep, 120 degrees Celsius water. So this requires 200 liters of this water per second to create 5 to 6 megawatts of continuous power to feed into the grid. The good thing about this, it's 24 hours a day, continuous power being put into the grid. But the fluid that comes out of the organic Rankine cycle engine, the geothermal liquid, it has to be re-injected at depth. And when it comes out of the ORC engine, it's still 65 degrees Celsius. So there's still a huge amount of heat if we could use it economically. Enhanced geothermal systems don't have porosity and permeability sufficient to flow fluids or to produce fluids. So we know that if you drill deep enough, you can always find high temperatures, even in northern Canada, which is exceptionally cool. But you have to bring that heat to the surface. We can't use it in the subsurface. It has to be used at the surface as heat and, of course, some electrical power. In the north of Canada, I assure you that the focus would be on the use of this for heat. So this requires hydraulic stimulation, establishment of communication between wells, and circulation of a fluid. Most people think the fluid will be water, but some people are doing research on the possibility of using supercritical carbon dioxide as a circulation fluid. To convert to useful energy, you have to put it through a power engine, as I mentioned, the organic Rankine engine and other cycles, or use the heat directly. As usual, there are geomechanics issues and environmental issues. You must manage your fluids appropriately so that surface contamination is avoided. And one of the issues that will arise in all deep geothermal projects is the potential for microseismic emissions. One very important area of research, in my view, is to bring together as much as we can from the geophysics domain to the rock mechanics domain or geomechanics domain, and to combine those knowledge bases so that we can in the future have better possibilities to predict the frequency, the rate, and the magnitude of microseismic events that arise because of the stress changes from cooling the rock mass. This is an important aspect of research in the EGS domain. So just again to reiterate, we have drilled some wells deep. These wells can be interconnected. We can circulate a fluid from one well to the other. The well bores are there to circulate the fluids and return the geothermal fluids back to the rock mass. To do this initially, you probably need stimulation. All of these dense rocks are naturally fractured. So it's not really a process of creating new fractures. What you're doing is opening up other fractures. So I prefer the term hydraulic stimulation of a naturally fractured rock mass. At the surface, we have processing into power and heat for the consumers. This is being done. This image is of the world's largest geothermal designed drilling rig. It can drill to 8 kilometers depth. It's not a conventional rotary rig. It's a rig that is designed to use hammer drills. Hammer drills are much more rapid in crystalline rocks, such as granite or very, very dense limestones. So the penetration rate of a hammer drill, a water hammer, as we call them, in granite can be 3 or 4 or 5 times more rapid than the penetration rate of a conventional oil field rotary drill. But we have to continue to improve that technology to drive the price down, because it's still very expensive to drill a very deep well. So in Finland, they have a project. The first well has been drilled. The second well is now being drilled to mine heat from depth over 7 kilometers deep, the geothermal fluids. What you see on the left, the building, is the old powerhouse. Because drilling costs increase exponentially with depth, and the heat present in the rock increases only linearly with depth, that puts severe limits to enhanced geothermal systems depth. You're never going to drill 20 kilometers deep. That is prohibitively expensive. It's never been done. The deepest hole in the world is only 12 kilometers deep. So we're trying to look at depths of several kilometers, maybe up to 7 or 8 kilometers, to mine the heat. We need well doublets. That means 2 or more wells for circulation. In the Finland project, it's 140 degrees Celsius, the temperature, so it's not that hot. And they're circulating water in a closed loop, but they're using the water 100% for district heating. They're not trying to generate power from it. And that's the most efficient use of geothermal energy if you can. Another technology that is being explored by a full-scale drilling project that is going on right now in Western Alberta, Central Alberta, is the EVER project, where they are installing an array of long horizontal wells to mine the heat from the rock mass without circulation of fluid through the rock itself, only circulation of fluid through the well bores. So the heat moves from the rock mass to the very long well bores conductively, and then it's brought to the surface for the generation of power. This is a difficult process, and we're all watching it carefully to see if the economics will make this process suitable. You need many wells. Conductive heat transfer to the fluids through the rock mass is a slow process. You need a closed loop and continuous recirculation so you do not waste any of the heat in the fluids. That means you'll need the best type of location for this would be a place of high temperature, of course. That's always the case in geothermal, but we need many wells that are long, and I'm speaking 3 kilometers long, perhaps 4 kilometers long. Another EGS research project that is going on right now in Utah, this is called the Forge project. Here in this picture, you see some of the drilling pads and some of the wells that have been installed already for seismic monitoring. And the injection well is being drilled, has been drilled on the yellow pad in the upper left, and they will be drilling an additional well soon. And if you look in the background, you see many wind turbines. Wind turbines are very irregular in terms of the heat output, but geothermal, in principle, can be much more regular than the renewable energy from wind turbines and from solar panels. So they're different quality, different use. So we have a naturally fractured rock mass. We do stimulation of that rock mass. The stimulation creates the ability to flow. But for those of you who are applied mathematicians in engineering or want to do mathematical simulation and modeling of this kind of process, I warn you, it is extremely complicated because the system parameters change with temperature and pressure, and they continue to change over time. As we have changes in effective stress in temperature and pressure, the governing equations start to behave extremely non-linearly because the bulk moduli, the elastic parameters, start to change as we open up the natural fractures in the rock mass, making a much, much more compressible large-scale rock mass, even though the rock itself at a small scale retains its original compressibility approximately. We have changes in the thermal response. We have changes in the porosity. It might not seem like much, but in a naturally fractured rock mass, the porosity might start at 0.1, and we might generate porosities as high as 1%. So that's an order of magnitude increase in porosity from the thermal cooling and the shrinkage. The permeability changes and the viscosities change. Even along the wellbore, the cool water goes in perhaps at 40 degrees Celsius and comes out at maybe 120 degrees Celsius. And that viscosity difference along the axis of the wellbore has a significant impact on the behavior of the wellbore. So if you go into this area, just be warned, it is very nonlinear. Okay, in summary, drill deep wells, do hydraulic stimulation, inject cool fluids, withdraw hot fluids, heat exchange to provide useful energy, and recirculation of the fluids. And we have to do these things correctly, making sure that we don't impair the infrastructure and that we have the approval of the local community. The next big role that the subsurface can play in the energy transition is the storage of energy. I mentioned natural gas storage, but we'll skip this. This is well understood already. I will mention compressed air energy storage and very briefly pumped hydro and maybe heat storage in the subsurface. Why do we need storage? We need storage to manage our power. We have to manage the power in a grid, whether the grid is a very small grid, like one small community in a remote area, or a huge grid like Southern Ontario, where we have 15 or 12 million people tied into the Southern Ontario grid. And our grid is tied into the United States, individual states around us, like Michigan and Ohio and New York. So grid management requires control of the voltage, control of the power input, and control of the frequency on a millisecond to second to day basis in order that the power be high quality, stable, at the right frequency, at the right voltage. Well, as we decarbonize our energy sources and shut down coal-fired power plants and oil-fired power plants and eventually natural gas-fired power plants, then we have to look at storage on a longer term, not just seconds, but hours and even weeks. And of course, climate issues dominate all of our thinking on these matters. So wind is intermittent. It's variable at all time scales. It's variable from second to second, from week to week. That means it's not dispatchable. In other words, it can't be just sent when needed. It can only be sent when available. So the generation costs in 2020 for wind power, just the generation costs are quite low. Now we're down to 2.5 to 5 cents per kilowatt hour. So this is now cheaper than almost all coal-fired power plants and natural gas-fired power plants. And it's much cheaper than other energy sources like nuclear, but there's an additional price, and that price is storage to try to make the power of better quality. So here's the problem. We see the red dotted line is the grid demand over 24 hours, the base load provided by, say, hydroelectric or nuclear is the double line close to the bottom. And the irregular line is wind power availability. And you can see that it's variable at time scales of seconds to days. It doesn't occur exactly when you need it, but you can, when it's available, take as much wind power and feed it directly into the grid, if you wish, to meet part of that grid demand. But the irregular component of that power, that wind energy, creates severe problems. So we're going to solve that using compressed air or batteries or pumped hydro. Well, solar power is also intermittent. It's also time variable. In a solar farm, when you have clouds that come in suddenly, your power generation can drop to 20% over the space of 30 seconds. It's not dispatchable either. The power is only available when the sun shines. So we have to find a way of storing it. The generation costs are estimated by published information for the year 2020 or 2021 to be in the range of 2 to 5 cents a kilowatt hour for modern installations. But last year, or actually early this year, the Saudi Arabian government signed a contract with a company that has agreed to build a solar system to provide energy, and the cost or their price is their price is 1.1 cent per kilowatt hour. I've got to get my numbers right here. 1.1 cent per kilowatt hour. And the United States Department of Energy has got a research funding project on with the goal of driving the cost of solar energy in the southwest of the United States, Nevada, Arizona, California, down to as low as 1 to 2 cents a kilowatt hour by in five years to 8 years. By 2030, the project expects the cost to be down in the range of 1 to 1.5 cents per kilowatt hour. We still need storage. We still need storage, so that the cost of solar power, the cost of wind power, involves the generation plus the storage. And we have a problem in countries where the variability can be dramatic. London in the United Kingdom, I put this graph on just to show the variability of the incident solar radiation in London over a number of years. And you can see that strong color there that is labeled variability. That's the variation from statistical variation from year to year, 96% of the. So you can see that it's hard to depend on solar power alone because of its variability in a given year. And probably in the United Kingdom, which doesn't have a lot of air conditioning, you still need a lot of electrical power. So we have this cyclicity. Now, if we look in December and January, you can see it's very difficult to generate significant amounts of solar power. So we have on a second by second, a day by day, a week by week, a month by month, and even a year by year variability in solar energy provision. That is a huge engineering challenge. So what we have to do is not only store the energy, that's the first word there, storage, we have to smooth the energy. We have to be able to take excess base load available from the nuclear power plants or the other type of base load systems we have and store it in our smoothing and storage facility to avoid wasting base energy. And we have to have the energy available on demand. That means it has to be dispatchable, and it has to ramp up when we need more demand and ramp down. It has to provide what we call inertia to the system, and on and on. And of course, naturally, we want to do all this while reducing the costs of energy provision. So it's a pretty huge challenge. Okay, so one way is batteries. This is the world's largest battery farm. It started operating in January of this year. It is huge. If I remember correctly, I may be wrong here. If I remember correctly, it's 250 megawatts is the power, and about or 300 megawatts is the power, and 1,200 megawatt hours is the amount of energy to be stored. So this is the world's largest battery farm by far, and it will be expanded. Well, batteries are great and they give good short-term response, but they're very expensive to store energy. You cannot ever expect a battery to store energy at 2 cents or 3 cents a kilowatt hour. Costs for batteries are in the range of 15 cents. There's a very wide range depending upon many factors. But the nice thing is that the efficiency is over 95%. Pumped hydro, it's great. Suitable elevation difference and water availability, no problem. There are land use issues because in places in very dense populations, people don't want valleys flooded, and there may be no other possibilities. The efficiency for pumped hydro is over 85%. Compressed air energy storage is the other technique that is suitable for grid scale storage. It's great, it's scalable, very low environmental impact, and it's versatile, but its energy efficiency is only 50 to 70%. What about hydrogen? Well, hydrogen is not yet ready for use as an energy storage medium. We probably are going to have to wait for an hour, for a generation for that. The concept is the following. Irregular power and excess grid power are stored as compressed air in an underground salt cavern or other repository. The heat of compression, hopefully we can store it and use it to heat up the air when we generate electrical power in the turbine. And that electrical power goes into the grid. Of course, some of the sun and wind power go into the grid directly as well during the day when it's needed. In principle, this can be done in a porous aquifer in the subsurface, but a porous aquifer is much more challenging than a salt cavern. Salt caverns have been around since the 1950s to store natural gas, and we now know how to build and construct a salt cavern effectively to make sure that it's stable and make sure that it is properly managed to store energy as compressed air. One of my graduate students originally from Taiwan, actually, Li, is doing some very sophisticated mathematics to simulate the dissolution of salt during the creation of the cavern. It's an extremely challenging multi-physics problem. The world's first adiabatic project, partly adiabatic, that means you're storing the heat from compression and you're using it to heat up the air, is now generating power in Ontario. It generates 1.75 megawatts of power. That's its maximum power generation capacity. And it stores about 8 or 9 megawatt hours of power. So it's very small. It's a demonstration project. It's in a salt cavern, and up to now it's had excellent performance. So this is just a cross section of the salt cavern from sonar. I would never ever use an old solution cavern if I could have my privilege of building a cavern in a good shape so that it's geomechanically more stable. This is the wellbore where compressed air goes in and out. And this is the facility in the background. The compression and expansion is on the left. And those tanks store the compression energy, the heat of compression, in a thermal oil. Another way of storing compressed air is using a cased wellbore. The nice thing about a cased wellbore in the subsurface is that when we put in a 30 centimeter or 38 centimeter diameter wellbore in a drilled well in granite or in shale or in limestone or in sandstone, this is independent of the geology. We can cement that steel cased well in place, and the surrounding earth provides the confinement. So now we can use that wellbore to store a gas up to maybe 40 or 50 megapascals, depending on the design, and up to 200 degrees Celsius. The well can be 500 meters deep, 1,500 meters deep. Deeper is unlikely. Generally speaking, for our calculations, we use a 1 kilometer deep well. And if you need more energy, well, you can use 2 or 4 or 10 of these wells. And each one can store approximately 6 to 10 megawatt hours per well. This means that this technology is quite scalable. In other words, you could have one modest well and a small system that would output just simply a quarter of a megawatt for a very small facility. Or you could have 20 or 30 wells to create a grid scale, large scale compressed air energy storage system. A system would look like this. I say would look because this is an image of gas wells, but it's exactly the same principle. This 4 wells that look like this would store 40 megawatts of megawatt hours of energy. And you can see that you could put 20 wells easily in a very small footprint, much smaller footprint than pumped hydro or other systems. The system operates in the following way. Air is brought in and compressed, sent for storage in this wellbore. On the right-hand side, energy recovery from the compressed air. The compressed air passes through turbines and it's heated up. Right now, there are 2 grid scale facilities in the world that do this, and they use fuel. They use natural gas to heat up the air to make sure it doesn't freeze as it goes through the turbines. In the adiabatic system that has been built, the small system that has been built in Ontario, it's the heat from the compression that is used to heat the air going into the turbines. This is a commercial scale compressor, and this is a commercial scale air pump, air engine actually, not an air turbine, but an air engine. It's kind of like a diesel motor that can drive a generator. So the compressed air solution, basically you take this very irregular power and you use storage as appropriately for the irregular part. And then you smooth the system so that the system sees this. It sees the excess power needs coming from those well bores. It doesn't see this, the yellow irregular pattern. Smoothing, and the good thing about compressed air turbines and compressed air engines is that they rotate at the right frequency to give you frequency control in the grid, and they can ramp up very quickly, giving you many megawatts of power very quickly, but of course not as quickly as a battery. We need batteries, but for a good energy storage system in the subsurface, 95 to 98% of the energy would be stored as compressed air, only 2 or 3% in batteries. But the combination of batteries and compressed air is very powerful to give you excellent quality energy in the grid. Compressed air energy storage smooths the power provision. Now, my final point is to talk a little bit about heat storage. We all know about conventional ground source heat pump geothermal systems. And the idea is in a climate like Toronto that in the winter we extract heat from the ground and that makes the ground get colder. But in the summer we extract cold from the ground, if you will, and then that warms up the ground. And that more or less balances. But this doesn't work in a hot climate, because in a hot climate, you don't want the heat, you only want the cold. So if you're mining the cold all the time, your ground is getting colder and colder and colder until the efficiency becomes very poor. It's the same thing in northern climates. You don't want heat, you don't want cold in the summer. You don't want air conditioning in the summer. You need heat in the winter. So if you extract heat every year, the ground gets colder and colder and colder. So that means that we have to have some way of storing heat, or the way I express it is recharging the thermal battery. We have to do heat geostorage to recharge the thermal battery. Now, there's many ways of doing this, and I'm not going to go into further detail, except that to say that if we have a heat geostorage system, we also have all of the geomechanics and the geology and the fluid issues that we have to contend with. There's a huge amount of geology and geomechanics that go into all of these projects. And we can integrate deep heat sources, like in my diagram here, I have a deep enhanced geothermal system repository. And I'm mining heat from that. I'm generating some power, but I'm also using some of the heat. But that's not all. I can, if I want, use other sources of waste heat from diesel power generation, from the exhaust from diesel engines, from excess wind and solar power in the summer, and I can create a shallow repository. And that's in the middle of the diagram there. And you notice I've drawn it as if it was a battery, because that's what it is. It's a heat battery. I'm storing heat there, and in a large volume repository, where the surface area is small compared to the amount of heat stored, we can store heat seasonally. So in other words, we can pump heat into the system in July and August and September, and extract that heat in December, January, February, March. So that's the concept of a thermal battery. And that will help us dramatically in places like the north, where we need the heat in the winter. But remember, if you have a method of cooling the ground, we can also cool the ground to store cool temperatures so that we can extract that for use in the summer in hot climates. My final slides are just using, for example, on the left here, an underground mine that has been abandoned, and we can install a pump house. And if we have an upper reservoir of water, we can pump excess electrical energy from the grid up to the upper reservoir when it's available. And when we need energy, we can use that liquid to pass through the turbines in the pump house, filling the mine, or not filling it to the surface, but up to some level, and repeating that process. The maximum power is a function of the volume rate, the density of water, the gravitational force, of course, and the delta Z, which is the elevation difference. These systems can achieve 85 to 90% efficiency in terms of energy inputs. The first project in Ontario is being proposed and is being assessed by local residents and by the government, and the studies are being done. It's about 200 kilometers, 250 kilometers northwest of Toronto. And the idea is to store on the highlands, well above Lake Huron, have an underground pump house with the pumps and the turbines, and have the water just exit to Lake Huron when, which is at a much lower elevation, 200 and some meters lower elevation. And then when excess energy is available, we can reverse the flow and pump water up to the storage pond. All right, I'm done the technical part of the discussion, but I do want to say that when we have energy storage issues, we have to look at the surface impacts. For example, that pump storage facility needs a pond at the surface of about 5 million cubic meters. We need in the subsurface to look at the mines, the caverns, the pump houses, saline aquifers, all of the geology and geomechanics. Thermal issues, because we're going to be heating the ground if we're storing heat, cooling the ground if we're mining heat. This is going to generate stress changes that will lead to microseismicity. We have to have ways of better understanding the issues associated with this so that we can have some predictive capability. We have to integrate these systems and so on. And it's a very rich area to work in. There are huge numbers of developments, of efficiencies, of optimizations, of integrating of different techniques together that are going to be examined by us, by our students, by people in this area, and implemented in countries around the world as time goes on to help the energy transition. So the subsurface can be used for storage, for heat sources, for disposal of waste, for sequestration of carbon. And all of these things are important elements in the energy transition that we're undergoing now. I'd like to acknowledge the people in Taiwan and that are involved in Project 111, specifically Professor Liang Weiguo, who spent a year at Waterloo some years ago, a very professional, respected person. I'd like to thank my students and colleagues, and I've listed a few of the students here that are doing work on relevant systems, thermal energy, heat transfer wells, induced seismicity. Some of my colleagues, Royden Fraser, Rob Gracie, Yuri Leonenko. And of course, some of the work has been supported or at least in cooperation with companies like Hydrostore and NRStore for the compressed air energy storage in Ontario, Cleantech Geomechanics for cased well energy storage, and Terralog Technologies for biosolids injection. Thank you for your attention. I'd be happy to answer any questions that you may have.
Thank you. Thank you. Yeah.
可以，能听见，能听见。
Diane, do you have any questions?
Hi, Professor. I think there have some questions from Northeast University from the chat panel. Do you see that?
Oh, in chat, there's a question. Okay, yeah. Thank you, Lee. Once I was told there are so many underground passages in the University of Waterloo, and can they connect, and that they all connect the buildings above the ground. That's correct. And they are used for water lines, for electrical lines, and for heating from the central heating station. We have a central heating plant. It burns natural gas and provides hot liquids that are circulated to all the buildings, okay? Now, those tunnels are only 5 meters deep, 6 meters deep. But that's our heating system as well. Now, our heating system uses natural gas to heat water. But if we had a geothermal source, or if we had other sources of heat, we could certainly use that for this circulation system. But the circulation system has no capacity whatsoever for storage. Another question, pre-existing natural fracture distribution in enhanced geothermal systems. That's a really challenging question. This is one of the most difficult things to do in engineering geology, is to determine what the natural fracture system geometry is. So there are some ways of doing this technically. One way of doing it technically, of course, is to core a well. So then the well might be at an angle, for example, of 20 degrees. And you obtain core and you look very carefully at the natural fractures and the distribution when you bring the core to surface. There's also some technology that has been developed by the geophysical service companies like Schlumberger. If you put a suitable geophysical signal emitter in a wellbore, sending out a sharp pulse of acoustic energy. That sharp pulse of acoustic energy becomes scattered by natural fractures. So there's what we call backscatter towards the sensors. So you measure the backscatter with a series of maybe 10 or 20 sensors along a borehole, maybe 20 meters long as you're logging, or 10 meters long. And they have developed ways of giving you at least a rough idea of some of the natural fracture geometries in the near borehole environment. Another approach, of course, that to try to understand the fracturing, the natural fracture behavior, the natural fracture geology, is doing surveys in deep mines, where you can actually see the natural fractures and make sure that it's a natural fracture as opposed to a fracture that you've generated by your mining. And then how do you bring this into mathematical modeling? Well, you've mentioned here in your question, can we use DFN models or DEM models, discrete element models, or discrete fracture network models to simulate? And the answer is yes, we can. But those models are very, very heavy computationally. So when we get to a large number of natural fractures in the model, execution time is very lengthy. So what some of us are doing, we do this kind of modeling, but we also, for the large scale, have generated what we call homogenized models. These models are actually based upon the discrete element methods, or they're methods of approximation, methods of homogenization, so that we treat the rock mass as a continuum rather than a fractured system. So it depends on the scale that you're working. If you're working on the scale of many hundreds of meters, volumes that might be a quarter of a cubic kilometer, you cannot put in the actual fractures. You have to put in, even with these fracture models, you have to put in a representative set. Or you can use this homogenization and upscaling technique to give you some information as if it was a continuum. But the properties of the continuum are changing as the temperatures change. Permeability of the system, the heat transfer rates of the system, all of these are changing so that all of these models are inherently highly nonlinear. But yes, we can do that. Salt caverns for gas storage. We use salt caverns for gas storage in Canada, in Saskatchewan and Alberta, where there is production of natural gas. But for here in Ontario, for gas storage, we're actually using small pinnacle reefs. So there are about 25 small pinnacle reefs. These are reefs that are sealed with shale, limestone reefs that are sealed with shale. And they're very small. They're only maybe a half a square kilometer in area, about 12% porosity. And that's where we store our natural gas here in Ontario, is in these reefs. There are salt beds in Ontario. The salt caverns are generally all vertical and they're small. We are not using salt caverns right now for large scale compressed air. In Germany and in the United States, where each of those countries has one large grid scale energy storage system in salt caverns, the caverns were created vertically. So one of the challenges we have in Ontario is that our salt beds are generally thinner, too thin to create a huge cavern vertically. So we want to create horizontal caverns. And that is one of the questions of my graduate student, Li from Taiwan, is to try to develop a mathematical approach to simulate the construction of caverns that are long, but with a limited cross section, so that you could have 1 million cubic meters in one cavern, for example. That's that's a kilometer long, but only maybe 35 or 40 meters in diameter along that length. The mudstone layers and other discontinuities should not affect the cavern operations for a horizontal cavern, because we're only putting in air and taking out air from the ends. So that if there is a roof fall or a problem like that, it's not going to twist the pipe. For vertical caverns, we try to design the cavern so that the upper part of the cavern is highly stable, and we are putting air in, remember, just at the top. We don't have a pipe going all the way down to the bottom, so that if there are mudstone layers or other geological discontinuities that are going to cause a rock fall, the pipe should be protected that way. Now, within the salt itself, we're not going to have any airflow because of capillarity and because of the extreme low permeability of salt. But yes, we have to look at those mudstone layers, and we have to look at other layers within the salt to make sure that they are capable of sustaining the pressure differential cyclically, on a daily cycle probably, for 30 years. So that means 10,000 cycles at least. So in a salt cavern, for example, 700 meters deep, your maximum pressure might be 14 megapascals, and your minimum pressure might be 5 megapascals. But you're cycling that day after day after day for 30 years. So we do have to understand whether what type of geomechanics issues arise, and whether we can sustain that seal, indefinitely. Yes. Yes, indeed. We have Professor Walk from Dalhousie University in Nova Scotia who's commented here. Salt caverns have been safely used for storage since the 1950s. The strategic oil reserve. China also has a strategic oil reserve in Jiangsu province. Yes, indeed. They are very suitable. Yes. Salt seals itself because of its high ductility and depth. We have a number here, 2,000 meters. In general, our storage facilities in salt will be from 400 meters to about 1,500 meters. One of the problems when salt at great depth, more than 2,000 meters, is that the salt is so ductile and so plastic that it limits our ability to pressure cycle. We have to have a narrower and narrower pressure cycle to avoid the salt cavern closing too rapidly by creep. And it's not just closing, it's also that when we have creep that is causing major cavern changes, then we start to have problems with deterioration of the non-salt beds, and maybe even threats to the pressure integrity of the cavern at the large scale. So in general, we're saying, 400 meters to maybe 1,500 meters depth is where that's the sweet spot. From the point of view of salt behavior, 800 to 1,200 meters seems to be ideal. That's where we can build caverns that are going to be extremely stable for long periods of time. The two commercial projects, the one in Germany has operated their salt caverns cyclically, day by day, for 37 years. So we know we can do it. Just as an additional comment here, I did talk about using cased wellbores, because salt caverns are great when you have them. So you have salt caverns in Jiangxi province, but you don't have salt caverns in Heilongjiang. So then you have to realize that salt is extremely limited in this geographical area. For example, Singapore would love to be able to store large amounts of energy under the ground. But of course, there's no salt in Singapore at all. And there's no salt nearby in Malaysia or Indonesia near enough that they could use. So if they want to use compressed air, probably subsurface wells is the appropriate way to do that.
Yes, there are many sources in vitro in fact. And what I can say about the seismic or microseismic result from fracturing. How could we avoid this kind of event during the fracturing, either hydraulic or CO2 or other technologies?
The sound is not coming through quite clearly, Wigwo. Is your question about the hydraulic?
Yes, hydraulic fracturing will result in earthquake or macro seismic. How to avoid
hydraulic fracturing in like granites and other rocks for geothermal work?
Yeah.
And the question is, I'm sorry.
Microseismic problems or earthquake problems.
Oh, yes. Yeah. Okay. Well, this is maybe one of the biggest unanswered questions that we have, Professor Liang, is can we predict the magnitude and the frequency, the number of events in a geothermal project where we are mining the heat? And the answer is right now, not very well at all. That's why I believe this is a really critical area for research. The next question is, are there techniques, are there methods that we could use to reduce the magnitude of a microseismic event? Like, for example, every 2 months, closing the production well and increasing the pressure inside of my geothermal area by 5 megapascals to trigger some seismicity under controlled conditions and then go back to operation. That's one idea. In other words, can we engineer stress in the subsurface? And I think that's another area of really potentially interesting research. Can we monitor the microseismicity more cheaply? Or do we have to drill a wellbore down, like 5 kilometers deep? Maybe we can, maybe we can use hammer technology to drill small diameter wellbores, maybe only 12 to 15 centimeters diameter wellbores quickly, like we do in the mining industry, but much more quickly. So then we can install seismic sensors and temperature sensors. And then that gives us more data right close to the sources that we can use for engineering management of the process. There's a huge number of questions related to this seismicity generation. And one of them has to do with risk. Now, unfortunately, the geothermal project in Basel, Switzerland, within a few days generated seismicity that could be felt. But if your geothermal project is far away from a heavily built up area, but by far away, I mean like, say 20 miles north of, 20 kilometers north of Beijing, say, where you're in the countryside. Well, your risks of any damage are extremely small because you don't have large buildings and large infrastructure that can be damaged. The microseismic activity in a geothermal project is fairly shallow. So it's not going to propagate and cause damage, far away. It's very local. So that means that the consequence of the microseismicity is quite low. But you're not going to create a geothermal project underneath the center of Taiyuan. You're going to try to locate it elsewhere. You're going to try to manage the seismicity. That question, Professor Liang, is wide open. We need some good engineering and some good science.
Yes, thank you. In fact, last week, we discussed with Professor Sonia, my tutor. He had an opinion that if the microseismic is good for it means avoiding large scale or large magnitude of the earthquake, maybe it's good.
Yes. Yeah.
If
Well, first of all, if we can live with it, right?
Yes.
Now, we have in Alberta, during hydraulic fracturing for shale gas, microseismic events or small earthquakes of magnitude 4.1, 4.2 were generated a few years ago.
Yes.
That doesn't happen anymore. That's because the companies have been subjected to a new set of regulations for injection and behavior and hydraulic fracture design. And we don't have those kind of events anymore. But those events were 300 kilometers away from Edmonton. There's no big buildings, there's no big infrastructure. In other words, the actual consequence of the microseismic event was zero on the infrastructure. Of course, people could feel it and people were nervous, but there was no impact at all. So these are the things you have to balance. Like I said, you're not going to create a geothermal project underneath Taiyuan because people will feel even small earthquakes. But out in the countryside, 20 kilometers north of Taiyuan, then you can probably manage it much more readily. Somebody else asked a question here about biosolids injection and whether or not the injection this biosolids injection process is the biological process that happens at depth is exactly the same as happens in surface biogas processing. Anaerobic bacteria, in other words, bacteria without oxygen, create the methane. And in the surface biogas process, you can generate the biogas, but then you still have a large amount of sludge and waste material that you have to dispose of. And that waste material contains a lot of carbon. So what do? Well, you spread that waste material on fields. But that waste material, if it's biosolids, it can contain inactivated viruses. It can contain heavy metals. It can it can even be contaminated with other liquids that have been dumped into the system. That happens a lot. So it's the same biological process at depth, except that all of the dangerous materials stay deep in the ground, as well as the carbon. Now, I think that there's many areas in China where deep biosolids injection would be a better alternative than surface treatment. And I'm thinking of sedimentary basins like the Songliao Basin, with huge cities like Shenyang, Harbin, Changchun. These cities could very well treat their biosolids with the deep injection because the geology is suitable. Now, in other places like Changsha, the geology is not so suitable. The rocks don't have the necessary porosity or permeability. So biosolids disposal also depends upon having good geological conditions. And many areas in China have, such as Taiwan, but many areas in China do not, such as Fujian province, for example, where you don't have the necessary sedimentary basins.
Okay.
Professor Grant from Nova Scotia points out that you can have passive geothermal projects beneath buildings in cities, especially passive heating and cooling, without injection, and that's absolutely true, and that is starting to be done now in cities like Toronto in Canada, where more and more of these high-rise buildings are actually putting in heat exchange wells, no injection, just heat exchange in and out of the rock mass to improve the efficiency of their heating and cooling systems. A question from Yongjun Yu. Can the in situ rock samples from EGS systems with a depth much larger than petroleum engineering? Can we go, I think the question is, can we go deeper than in petroleum engineering? Yes, but one of the biggest barriers to geothermal energy is the cost of drilling. You see, in the petroleum and natural gas, you're producing a very, very valuable high energy product. So you can drill a hole no matter what it costs almost. I mean, some of the drilling offshore in the ocean, you know, it's $60 million for one well. Well, geothermal is very low grade energy. The amount of energy per cubic meter of warm water is extremely small compared to a cubic meter of crude oil. So we cannot afford to drill extremely expensive wells and to do extremely expensive hydraulic stimulation. We have to find better drilling. We have to improve our drilling techniques with automation, high-speed water jets, water hammers, or maybe some new technology so that we can drill in granites and other crystalline rocks cheaply, rapidly. Otherwise, it's not very economic. So yeah, we can drill to any depth you want, but the shallower the better from the point of view of cost. The petroleum industry has a lot to bring to this, for sure, but the mining industry as well, because it's the mining industry that has developed hammer drilling techniques for drilling in granites. And of course, in many laboratories around the world and many universities now, they are building laboratories to be able to do better experiments on thermo hydromechanical coupled experiments for the to try to get better predictions in geothermal systems. But I think that we need some shallow experiments where we can afford to put sensors and see if we can predict the behavior for 5 years and then confirm that behavior with sensors and good engineering data analysis. And I think we need those experiments to try to help perfect improve our tools for microseismic predictions, for the prediction of the thermal efficiency, for these other factors. Again, a very rich area for research and development. Yes, okay, great. Okay. I think that's all the questions, and it's 9:30 in the morning here, and that means it's 9:30 at night in Taiwan. So I'm going to thank Professor Liang Weiguo and Niu Dong and others that arranged for this. I believe that the session is being recorded, and I would appreciate being given a link to the recording, because I would like to have the recording posted on our website here in Canada.
Thank you.
Okay, bye.
Hi, Maurice.
Bye.
梁老师，再见。
再见。先过了。
啊，
你过来。
哈哈，我还在家里呢。好，梁老师再见啊。
好，再见。
再见，李丽，再见。
拜拜。再见，说再见，拜拜。
好，李丽，再见。
嗯哼。
你还在听他说吗？